This tutorial will show how to use Film QA Pro to do a radiochromic film calibration. You'll be using one of the calibration film images included with the Film QA Pro installation, and you'll find this one in Program Files / Ashland Advanced Materials / Film QA Pro / Image / Example EBT3 Rapid Arc. Calibration films can be loaded from File, as in this example, or they could be scanned into the application. If you're acquiring calibration films via scanning, consult the tutorial module on scanning. When you open Film QA Pro, the first screen should look like this, but depending on your configuration, it may have loaded the last case being worked on. In that case, click on File on the menu bar and New Empty Case to start a new case. In the Case Data Selector window, which is the window on the left, click the plus sign by Case Object Management at the bottom of the case tree and click Add New Case Object. There are two calibration objects in the list: Film Calibration Ordinary and Film Calibration Mosaic. And in this example, we'll be using Film Calibration Ordinary. But there's another folder in the installation package, Example EBT2 IMRT, that contains images you could use to practice mosaic calibration. To distinguish Film Calibration Ordinary from Film Calibration Mosaic, the former can only be used when all the films or patches required for the calibration are in a single image. The mosaic can be used for any calibration image, but is particularly useful where there are multiple images. The mosaic feature tiles all the images together to simplify the defining of the regions of interest or measurement areas. Click on Film Calibration Ordinary, and when the Film Calibration object appears in the case tree, click the plus sign to expand the object, and then right-click the line Calibration Film Empty. From the menu panel that appears, select Open Image Calibration Film from File. Navigate to Program Files / Ashland Advanced Materials / Film QA Pro 2013 / Image / Example EBT3 Rapid Arc, and open the TIFF file that begins 0_69_2. The file name embeds the calibration values 0, 69.2, 138.3, and 368.8 centigrade, but they're also available in the file exposures.txt in the same folder. When the TIFF file loads, a thumbnail image appears in the Film Calibration object. Click on the thumbnail to display it in the image window. The technique of having all calibration films in a single scan is called one-scan calibration. Not only does it minimize the number of calibration images, but it also uses your film and time efficiently. Because Film QA Pro uses rational asymptotic fitting functions that behave like film, that is, the responses approach constant values at high dose, just as the darkening of the film gets progressively smaller with each dose increment, fewer data points are needed to correlate the specific response behavior of film to dose. One of the most useful fitting functions is expressed as response equals A plus B divided by dose minus C, where A, B, and C are the coefficients to be determined. Responses for each color channel are fitted separately, but since there are only 3 coefficients for each channel, as few as 3 dose points plus the corresponding RGB response values are needed to make the correlation. However, we advise adding 1 or 2 extra points, since that allows calculation of statistics to show the goodness of the fit. and this helps in selecting the best fitting function, as well as to see if a dose point is in error. To fit all the calibration films in a single scan requires using pieces much smaller than 8 inches by 10 inches. And a good way of doing this is to cut strips 8 inches long and about 1 to 2 inches wide. Not only does this preserve an important clue as to the orientation of the strips to the sheet, but it also means that a set of calibration films can consume less than a single sheet of film, since it only requires 3 or 4 exposures plus an unexposed film. A recommended way of exposing film is to use a 10 centimeter by 10 centimeter flat field, and with knowledge of the dose per MU for a particular geometry, beam energy and build-up configuration, to deliver a known number of MU to the film. While the example you are working on doesn't conform exactly to this rule, it works best to have non-zero doses in approximate geometric progression rather than arithmetic progression. For example, 75, 100 and 300 centigrade rather than 100, 200 and 300 centigrade. Click on the image scaling icon in the toolbar to select Scanner Coordinates. The display changes to show the position of the films on the scanner. If you scan through FilmQA Pro and the Twain interface to Epson Scan, the image always contains the information of film placement on the scanner, and this is invaluable when investigating film dosimetry problems. The feature is not available if you don't scan through FilmQA Pro. At this stage, you could stay with the display and scanner coordinates, or use the image scaling icon to toggle back to top left origin display. Now use the frame selector tool at the top of the toolbar to draw areas of interest in the center of each film. Having drawn one frame, it can easily be duplicated. Using the mouse, hold down the Control key, point the cursor where the new frame is to go and click. In calibration, you are defining the average response of the film, so the measurement area should not be tiny. And experience has shown that an area of 20 square centimeters is sufficient. Now activate the calibration tool by clicking on the last line of the film calibration object. A display appears in the analysis window. Now click on the 1, 2, 3 icon in the lower right corner to populate the calibration table with response values. Then click in the dose column and enter the dose values. Note that you can enter the dose values in any order, as the doses and response values are sorted or matched in reverse order depending upon the responses. That is, the smallest dose is matched to the largest response value. By default, this uses the red color channel for synchronization, but other color channels could be used for this sorting, which could be selected in matching order or turned off as needed. Instead of manual entry of the dose values, they could be copied from a table, such as the one in the file exposures.txt, and then pasted into the dose column. As soon as the calibration table is complete, the data points and fitting functions are charted in the calibration window. The dose unit in the table and calibration plot in this example is centigrade, and the response values for each color channel are 16-bit numbers between 0, representing black, and the value 65,535, which corresponds to the light intensity on the scanner with no film present. Right-click on the dose column of the table or the dose axis in the chart and specify the radiation absorbed dose unit. Right-click on any response value column or near the response value axis on the chart to change the color channel response unit. The major choices are a 16-bit value, optical density, and percent. Optical density is defined as minus log 10 of the 16-bit value divided by 65,535. And the response percent is defined as the 16-bit value divided by 65,535 times 100. The fitting function is displayed in the window just above the calibration table. There are several choices in addition to the default. Click on the right side of the calibration function window to see a pull-out menu with all the choices. Use the calibration statistics icon just under the calibration table to display a table of calibration statistics in the image window. This is a table of consistency values determined from the measured calibration doses and the fitted values, and provides help to select the best fitting function for the data points. Lower values in the table signify a better fit. In this case, and most cases with doses up to about 500 centigrade, the best fitting function is usually the color reciprocal linear function. But for higher dose ranges up to about 10 gray, the color rational linear function is often preferred. And for even greater dose ranges up to 30 gray or more, the rational quadratic or cubic functions are usually best. Right-click on the line Calibration Model Equation under the Calibration Function window and select Copy Calibration Function Parameters to copy the coefficients for all color channels to another application. The fitting functions are generally expressed as either response as a function of dose or the inverse dose as a function of response, where the response values are expressed as percent, that is, the 16-bit value divided by 65,535, and dose is given in gray. The exponential universal calibration is a generic or pre-shaped function determined by compounding calibration data from many production lots of EBT-type films. It may better represent the shape of the response curve of these films, and in this way make it better adapted to the characteristics of any one lot than the other fitting functions. When the calibration is finished, there are a number of save options. Click File on the menu bar and Save Treatment Case As to save the entire case. Or save the calibration data by clicking on Film Calibration and choosing Save Film Calibration Data as Treatment Object. The calibration curve, calibration table, calibration function, and scanned images will be filed for use in calculating a dose map in this or any future case. When a calibration treatment object is reloaded, the calibration can still be edited. Alternatively, choose Export and select Save as Fixed Calibration. The calibration will be saved for use in calculating a dose map, but for security, a fixed calibration can never be edited or revised. This concludes the dosimetry tutorial. Other tutorials are available to fully explain scanning, dose map calculation, dose to plan comparison, as well as the tools for machine QA analysis.